Hello everyone. Happy Friday. Welcome to the TVE Happy Math Hour weekly interactive math reviews for Math 1314 and Math 1324, presented by Ms. Yvette Chuca, Mr. Ruben Carrizales, and Mr. Albert Isasi. Our session will actually be starting soon. This session will be recorded so that you may come back later if you need to, and so others who might have missed today's events will also be able to watch it. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with the information that we'll be sharing today. I'm gonna go ahead and send the link for the Math 1324 room for those who need to go to that room right there. And without any further ado, let me go ahead and pass it to Ms. Chuca, Mr. Carrizales, and Mr. Isasi so they can start their presentation. Thank you.
Hello, everyone. I hope everyone's doing well. We are going to get started shortly, so let's just give a few seconds to those who are transferring to the Math 1324 with Mr. Um, Albert Assisi. And we'll get started shortly with our exponential and logarithmic functions for Math 1314. Okay, very good. So as in continuation of this session that we did last time, we're going to continue and dive into a little bit more detail on exponential and logarithmic functions. So let's go ahead and get started. So first, let's look at the definition of an exponential function. So a exponential function, of course, has an exponent, and in this case is x, and the exponent is tied into the base, okay? And in this case, we have the variable a. Now, hopefully we're all familiar now that the domain of a function is all the input values, all the x values that a function can take. And for our exponential function, the set of the domain is a set of all real numbers. Compared to the range again of a function is our output, meaning our y values. And our y values for an exponential function is a set of all positive real numbers, okay? All right, so let's go ahead and look at some examples. So if we see here, if we wanted to examine the graph of this function is equal to 2 to the x. This is an exponential function. We have an exponent x, and in this case, our base is 2, okay? So if we wanted to graph, what we can do is we can do a table, okay? We select random values for x, and in my case, I just chose from -4 to 2, the intervals between those numbers. And again, to get my y values, my output, I just plugged in the values into the x, right? So a -4, plug it into the x, again, we get 1/16. Okay, -3, we get 1/8, and so on and so forth. So when we plug it in, okay, I want to show you how it's clear that our domain here, okay, even though this is a graph from a calculator, okay, our graph goes forever to the left and goes forever to the right. So our domain is all real numbers. If we're talking about interval notation, we're talking of all the numbers going from -infinity to +infinity. And we can also see the range very clearly. You see that our graph doesn't cross our x-axis. It's all above the x-axis, so we have only positive values. So our range in interval notation for our exponential functions is from 0, not including 0, all the way up to +infinity. Excuse me. It goes up, okay? Now, let's put all this together, okay? Let's look a little bit more detailed on this exponential function, okay? Again, looking at it, we have a base and an exponent, okay? Our graph of our base has to be greater than 1, okay? The domain, again, is all real numbers, or in interval notation from -infinity to +infinity. Our range is from 0 to infinity, meaning just the positive numbers, okay? Our parent exponential function will have a y-intercept always at y equals 1, or our coordinate system 0, 1, okay? We know that we read graphs from left to right, just the same way we read books, okay? So this graph is increasing. As I go from left to right, the graph is increasing, okay? Now, we've studied a little bit asymptotes before, and our exponential function has a horizontal asymptote, and it's here at x equals 0. This means that this graph will never cross or touch the x-axis. It will never become 0 or cross it or touch it. Okay, so continuous. What does continuous mean? Continuous means that our graph will not have any breaks throughout. Okay, there's no gaps or anything like that. It's continuous. If we were to draw with a pencil, we could draw it without ever lifting the pencil. Okay, so that's what continuous means. So let's look at this other example. What if our exponent was negative? Okay, we can rewrite this using our properties of exponents and rewrite 2 to the negative x as 1 over 2 to the x, okay, as a fraction. So on this graph, you see we reversed it. Our function that we looked before, okay, had a positive x. It was increasing. Now, if we have a negative exponent, we're going backwards, right? We are decreasing. It's the opposite. So let's look at its characteristics. The domain is not going to change, okay? It's still from negative infinity to positive infinity, goes forever to the left, goes forever to the right. Our range also did not change. It's still all the positive values, so from 0 to positive infinity. Our y-intercept, again, did not change. It's 0, 1. But what it changed was the the slope of this, right? It's decreasing, okay? We still have an x-axis horizontal asymptote. Again, it's not crossing our x-axis, and it's still continuous, okay? All right. So let's look at this graph. What do you think is going to happen now if I change the base, okay? So to see it, let's go ahead and plot a few points. Let's go ahead and do a table again for us. And once we do our table, we see that when we plug in these points, our curve on our graph is a lot steeper. And this is what's going to happen when our base increases. Our exponential function is going to grow a lot faster. That's why when you hear those terms, hey, this is going to grow exponentially, because that's what exponent functions do. They grow really, really fast when you increase the base, okay? All right, so if I were to do it on a calculator again, to see the graph of y equals 3 to the exponent x, okay? Again, it's not crossing my x-axis. It's still going to cross at the y-intercept at 0, 1, 0 for the x value, 1 for the y-intercept, okay? And it's also, it was a positive exponent, so it's increasing, okay? All right, so to continue practicing, let's look at this one. Let's increase the base one more time to the 4, but let's give it a negative exponent. Again, putting a negative exponent is going to reflect the graph on the y-axis. So instead of increasing, it's going to be now decreasing, okay? It's still, because we are not changing the base or doing anything with the base, again, our y-intercept will continue being 0, 1, okay? Again, we still have a horizontal asymptote at x equals 0. Okay, so let's look at some more properties. We had studied last time some properties of exponential functions. Let's look at a few more, okay? And these aren't really properties, we like to call them laws, right? So let's look at the product law first. So when we have two exponent functions that have the same base, we can add the exponents together, okay? Inversely, if we have two exponential functions that are being divided, well, opposite of multiplication is division, opposite of addition would be subtraction. So to simplify a division of two exponential functions that have the same base, we will subtract their exponents, okay? Then we also have what's called the power law, that if we have an exponent, an exponential function, and we take it to another exponent, we're going to multiply the exponents, okay? And then we can also have the distributive property for the power, okay? That if we have a product being taken to an exponent, this is the same thing as the product of each base being to the given exponent, okay? Same thing for the division. If we have a fraction that is being taken to an exponent, we have the quotient of each exponential function to the given exponent, okay? Now, x can never be 0 because if we have an exponent of 0, the answer will always be 1. So keep in mind that any number, any base to an exponent 0, you're always going to get 1. Now, we had studied before one-to-one relationships, and these laws also have a one-to-one relationship. And it says this, that if we have a function a equal to another function b, the only way that these two functions can be equal to each other is if they have the same base. If they're both the same base, then that means that for them to be equal with the same base, that means that also the exponents have to be the same. And I hope it makes sense that for these two things to be equal to each other, base a to the best to an exponent x has to be the same thing as the base b to the exponent x, okay? And we're going to see some examples of this. So again, this is what's called our one-to-one property for exponents. And this is very useful to solving exponential functions. Again, we encourage you to learn this property well because it comes in handy more times than not. Okay, so let's look at this example. Solve the equation for x. So if you see here, can we use the one-to-one property? The answer would be yes, because we have two exponential problems that have the same base. I have a base of 10, have a base of 10. So then I can use my one-to-one property, says that for these two exponential functions or equations to be equal to each other, then that means also the inputs have to be the same. So that's what I'm going to do. That 2 minus 4x has to be equal to 6x minus 1. So then all I have to do is a little algebra to solve for x. So I like to move anything that has a variable to the left and anything that has a number to the right. So here I'm going to move the 6x to the other side. So I do that by subtracting a minus 6x on both sides. And to move the 2 to the other side, I'm going to subtract the 2 on both sides. And when I do that, I get a negative 10x is equal to a negative 3. So now just to solve for x, I'm going to divide both sides by a negative 10. And when I do that, a negative divided by a negative is a positive, and x is equal to 3 over 10. And as you can see, I was able to solve for x using my one-to-one property for exponents. Any questions? Please feel free to ask me. Sometimes I go very fast, so please slow me down or ask me if you have any questions. So let's move on. How about this one? Can we solve this one and can we use the one-to-one property? But if you notice, wait, Mr. Carrizales, this one doesn't have the same base as the other side. One has a base 4 and we have a number of just 64. But hey, what I can do is I can convert the 64 into an exponential equation. I can say that I can rewrite my 64 into a base 4, and I wanted to use a base 4 because I have a base 4 on the left, and I know that if I take 4 to the exponent 3, this is going to give me 64. So 4 times 4 is 16. 16 times 4 is going to give me the 64. So now the answer is yes. Now I can apply my one-to-one property. For these two equations to be equal to each other, then that means that their exponents also have to be equal to each other. So then what I'm going to do is I'm going to set the exponents equal to each other. I have x plus 1, the exponent from the first equation, equal to the exponent of the other side of the equation. So to solve for x, I'm just going to subtract 1 on both sides. And it's a plus here, so this should be a negative, not a plus. Okay, so this is negative. So this is negative. So when I subtract the 1 on both sides, 3 minus 1 will give me the 2. Okay? Awesome. So let's go ahead and look at another example. Um, oops, and I went too far. But as you can see, if we were to ask ourselves, can we use our one-to-one property for this one? Well, I have a base of 5 on this side, but I have a fraction on here. So just a quick view on how I went from here to here. And what I did is I first converted my 125 into a exponent part. I have 5 cubed, right? So 5 cubed is going to give me 125. 5 times 5 is 25. 25 times 5 is 125. Then I use my exponent laws to move my base up. It's going to give me 5 to the negative 3. Yes? So now I can apply my one-to-one property. My one-to-one property tells me that for these two exponent equations to be equal to each other, then that means that their exponents also have to be equal to each other. So we have x minus 3 is equal to negative 3. To solve for x, I'm going to add 3 on both sides. And when I do that, I have x is equal to 0. Okay, and it's always good to check your answers. If I would put here 0, 0 minus 3 is going to give me a negative 3, and 5 to the negative 3 is going to give me that 1 over 125. Okay? Always check your work. All right. So let's look at another exponential function that works the same way, but we want to look at the base e exponential function. And this base e exponential function is very similar and has all the same laws and properties that we just talked about, but we use symbols. And most of the time, the reason or when we use the base e exponential function is for business, okay? But it's called the natural base, okay? The natural base is an irrational number, just like the very familiar irrational number is pi. Like pi is a symbol that represents 3.14 blah blah blah. Well, same thing here. E is a symbol that represents 2.7182 blah blah blah. Okay, so this is called the natural exponential function, and it has all the same properties and characteristics as before. Okay, you see here it has a horizontal asymptote at x equals 0, doesn't cross my x-axis. It has a y-intercept at y equals 1, or the coordinate point 0, 1, okay? And it's increasing and it's continuous, okay? So don't be afraid of this one. It's the very same exponential functions that we see. It's just it's called the natural exponential function, okay? All right, so again, if we were looking at the same characteristics, if we have a negative exponent, then we flip it. We have a reflection on the y-axis. So instead of increasing, it is decreasing, okay? It's still continuous. It still has the same domain from negative infinity to positive infinity, and the range is still the same. All positive values from 0 to infinity, okay? All right, so let's go ahead and solve for this one. So if we see here, oh, we can apply our one-to-one property again. These two equations have the same base. And in order for these two equations to be equal to each other, then that means that their exponents also have to be equal to each other. So what I'll do is use my one-to-one property to solve for x. So I'll set x squared minus 3 is equal to 2x, and I'm going to solve for x. Now, hopefully you all see that, I have a square, right? So we have a quadratic function here. So to solve for this, again, I like to move everything to one side, okay? Set it equal to 0. So I'll move my 2x to the other side. It's going to give me x squared minus 2x minus 3 is equal to 0. So we've studied a lot of ways to solve quadratics. We can factor it. We can use a quadratic formula. I always like to factor. I think that's the easiest way to solve things. So if I factor the x squared minus 2x minus 3, this is going to give me x minus 3 times x plus 1 is equal to 0. So now I use my 0 property, right? That in order for when I multiply two numbers, the only way that the product of two numbers becomes 0, that's if either this part is 0 or this part is 0. So I solve for x. X minus 3 is equal to 0, or x plus 1 is equal to 0. And I find that I have x is equal to 3 and x is equal to negative 1. But we always want to check our work. We want to make sure that the values that we put in are valid, yes? So again, we would plug in these values back here to see that we do get a match, yes? All right, any questions before I move on forward? Okay, very good. So let's look at a very, very famous exponential function, okay? And I like this function a lot because you may not realize it, but you use it every single day. If you have a bank account, if you ever purchase a car, this is the formula that the company is going to use to calculate either your payments, your interest, how much you're going to owe at the end of so many years. So very, very important formula, and it's called the compound interest formula, okay? So let's look at some of the variables that are used in this formula, okay? I'll give you a little insight on business. A stands for annuity, but the way I like to think of this A for this class is think of the A as a future value. It's the money that I'm gonna have after I apply interest and after so many years, okay? So I want you to consider the A as your future value, okay? P in business is considered your principal. But the way I want you to think about it, and there's a typo here, I want you to think of this as your present value, not future, but present value, okay? Your P should be present value, okay? All right, let's look at some of the other variables. R refers to your interest, okay? Whenever you're going to be dealing with word problems, they're going to give you the interest in percent. And when we're going to use it in the formula, we got to make sure we convert the percent into decimal format, okay? So R is considered your annual interest rate, and N represents the compounding periods or the terms that we're going to do it in a year, okay? And there's several that we want to look at, and we're going to go over them shortly. And the last variable to consider is T in our equation. Okay, T is going to refer to the number of years. So one of the things that I want you to also to focus on is that this formula is based on a year. Okay, everything is relative to a year's time, periods per year, numbers of years. Okay, it's relative to years. So that's where the N comes in, because we can cut up the year into several payments. So let's look at some of the options that we have, our compounding periods. Okay, so whenever you have a word problem and they tell you that you're going to use the compound interest formula semi-annually, that means that it's going to be applied twice a year. So my N is going to be equal to 2. Okay, if they tell you that they're going to apply the interest formula quarterly, I always like to remember, think of quarterly. How many quarters are there in a dollar? 4. So quarterly means 4 times a year. N equals to 4. Okay, then you might say monthly. Your payments are going to be done monthly. Well, monthly means every month, and there's 12 months in a year, so N is going to be 12. And then they might say they're going to do the interest daily. So there is 365 days in a year, so N is going to be 365, okay? So let's look at how we can apply our compound periods to our formula, okay? So you see, we're going to do a fraction in order to get this compound period together. So let's look at our first word problem, compound interest problem. Find the amount to which $1,500 will grow if deposited in a bank at 5.75% interest compounded quarterly for 5 years. Okay, so let's stop and think for a little bit. So they're telling us that we are going to deposit our present value. We're going to deposit $1,500, and what they want us to find out is what's going to be our future value. So what they're asking us to solve for is the A value. okay, or I mean the a variable. So let's write down what they're giving us, okay? They're giving us p, our present value, 1,500. I converted my 5.75% into decimal format, which is 0.0575. Again, they told me that the interest is compounded quarterly, so that means n equals to 4, and they're telling me that it's been taken for 5 years. So my t is equal to 5. All right, so let's go ahead and substitute these numbers into our equation. Okay, our equation for the compound interest is a is equal to p times 1 plus r over n times t. Okay, now, if you're gonna do this with your calculator, you gotta be careful, gotta make sure you use the right number of parentheses. Um, so I always like to break it apart just to make sure that I solve it correctly. Okay, so let's go ahead and plug in our what we know. We know the P, which is the 1,500. We know the R, we know the N, and we know the T. Okay, so the way I would do it, okay, if I were to do it on my own, okay, I would first do what's inside the parentheses first. I would do 0.0575 divided by 4. Hit enter on my calculator. I'm going to add 1 to that. Then I get my answer. So to that answer, I'm going to take it to the exponent 20 because 4 times 5 is 20. So hit enter. Once I hit enter, then I'm going to multiply this answer to 1,500. Now, keep in mind, WebAssign will be specific on how they want you to answer. Okay, let's say if they ask you to round to the nearest cent, again, we're talking about money here. So cent means it's going to be 2 decimal places, right? 55. Now, there's some times where they tell you that they want you to round to the nearest whole number. So then the answer would have been 1,996. Okay, so just be very careful in reading how they want you to submit your answers and in your rounding. Every time they mean cents, means 2 decimal places. Okay, all right. Let's go ahead and do another example, finance problem. So a couple just had a baby. How much should they invest now at 5.8% compounded daily in order to have $35,000 for the child's education 18 years from now? So what they want is they want to have $35,000 for the future. So they are giving me the future value that they want. And what they want to find out is they're saying how much should they invest now. So what they are asking for me to get is the present value, the p value. So and I got the rest. They're giving me the r, the interest rate, which is 5.8. They're giving me the n, which is they said that is daily. So we're going to use a 365, and they're giving me the t, 18 years. So let's go ahead and do this problem again and solve now for P, because that's what they want us to find out. How much do they want to invest now? My present value. Okay, so these are the knowns, my A, my R, my N, and my T. Let's go ahead and plug it into the formula. Again, the way I would do it is I would do the division first. I would do the 0.058 divided by 365 first. Then I would add 1 to it. Okay, I think I did it here. Then I would add 1 to this. It's going to give me 1.00158904. Again, 365 times 18. I would have used my calculator for that. Okay, it gives me 6570. So then now on my calculator, I'll put all these values. So, and I'm glad, and let me stop here. When you're doing these problems, okay, you're dealing with exponential functions, and I had stated for you before, it's like, you know how that comment that they say that things grow exponentially, that means that if you change a decimal value, your number can change dramatically. So when you're doing these problems on your own, you don't ever want to round until you get until the end. Don't round as you go, because then your answers are going to be way off. Okay, you always want to use all the numbers that your calculator is giving you and do not round until the end. Okay, so I would put all these values into my calculator and take it to the exponent 6570, and it's going to give me this value, 2.840320963. Okay, so to solve for p, I'm going to divide this number on both sides. Okay, so P is equal to 35,000 divided by 2.403200963. And when I do this again, because I'm dealing with money, they weren't specific. I'm just going to round to the nearest cent. So the couple should invest $12,322.55. That way they can have $35,000 18 years from now. Okay. Any questions so far? All right, let's keep on moving forward. All right, so a recap. Okay, we can see two compound interest formulas, which is this one, the simple interest or the annual interest formula, and we could also have what's called the continuous compound interest formula. Okay, and then in this one in particular, you see that we are using our natural base e, okay, our e exponent to solve for continuous compound interest. So when in your homework they ask you what is the interest compounded continuously, you're going to use this formula. Again, your P still stands for your present value, your A is still your future value, your R is your interest rate, and T is your time. Again, but because it's continuous, we're no longer cutting it through the year. So there's no more compounding period, okay? All right, so let's look at what's called the inverse of an exponential function, which are now the logarithmic functions, the opposite, right? So the a logarithmic function, just like an exponential function, we can use our one-to-one properties, okay? And so the best way to see these in action is to look at examples. But before I get into that, just like before, okay? Look, our exponential functions had a horizontal asymptote, right? So on our logarithmic functions, the first thing that we want to do is, or you need to know, is that these are going to have a vertical asymptote, the opposite. Now, one thing that you need to be familiar is that when we're looking at logs, we got to make sure that we're dealing with a function. So you always want to do the horizontal line test in order to double check that our function does have an inverse or is or we can apply the one-to-one. Okay. So given that example, are these functions one-to-one? So if we look at A here, if we do our horizontal line test, our horizontal line test means that our graph would only cross the graph once. But what about B? If we do B and you do a horizontal line test, then this graph cannot be one-to-one. This graph does not have an inverse because, again, it crosses the graph twice, okay? So keep in mind that you always want to check this. So when we are dealing with a one-to-one, we may have to alter our domain in order for us to find the inverse or be able to apply our properties for logs, okay? So let's review again the exponential functions so you can see how they're inverses of each other, okay? So these are the exponential functions that we just saw. Y is equal to 2 to the x has an exponent x base 2, and this is my graph, okay? Now, let's compare it to a log function, okay? On here, my base is 2 on my exponential function. So for it to have an inverse of a log, you see how logs also have a base. So the base here is 2. Here on an exponential function, my input value is the x and I have an output value for the y. You can look at it as backwards now, right? Here you can still also put an input value for the log, but you're gonna get a y value out, okay? So for us to use also one-to-one properties within each other, or for these to be the inverses of each other, they have to match these, okay? The bases have to be the same, and the input of one has to be the output of the other in order for them to be one-to-one, okay? So let's look at it with a table so you can see what I mean, okay? So if I see here, if my input here is -3 for my exponential function, look what I get here. I get 1 to the 8. Now, if I here have my output is -3, do you see that my x value is 1/8? See, they're opposites. So if my input is -2, my output is going to be 1/4. And for my log function, if my input is 1/4, then my output is -2. Okay? So these are reverse values, and this is just to show you how these two functions are inverses of each other, are opposites of each other. Okay? All right. If I were to graph them, okay, again, my exponential function is an increasing function. It has a horizontal asymptote, okay? Um, and if I look at my log function is also an increasing function, but it has a vertical asymptote, okay? Also, the exponential function has a y-intercept at y equals 0. My exponential function has an, what's opposite to a y? X. Well, the log function has a x-intercept at x equals 1, okay? So keep these things in mind. All right, so let's look at more details of both of them. Okay, on my exponential function, we have our domain range, y-intercept. It has a horizontal asymptote at the x-axis. Opposite, look, everything's backwards. The domain of the exponent is the range of the log. The range of the exponent is the domain of the log. Okay, so the domain of the log is all positive numbers from 0 to infinity. The range is all real numbers, and these are supposed to be backwards. Okay, they're flipped. It's supposed to be from negative infinity to positive infinity. Okay, instead of having a y-intercept, I have an x-intercept at 1, 0, and it has a vertical asymptote. The y-axis is its asymptote. Okay. All right. So again, continuing with or equivalency or using the one-to-one, okay, which I already covered. For these to be the same, okay, they have to have the same base, okay. The input of one has to be the output of the other. The input of the other has to be the output of the other, okay. So let's go ahead and um, look at some common logs, okay. Remember, whenever they don't write a base, we're always going to assume that it's a base 10, okay? Base 10 logs are equal to our natural log, okay, which is the ln, which is the, again, the business version of our e-base, okay, the natural log. All right, so let's go ahead and solve by converting our logs into exponents. And this is an awesome tool to solve for a log function by converting it to an exponential function, okay? So here we have log a base 4, input 16 is equal to x. So if I want to convert this log into an exponential problem, again, my base of this log is 4, so my exponent is gonna have a base 4. The input of the log is going to be the output of the exponent, and the output of the log is going to be the input of the exponent. So now I could use my one-to-one property. If I really wanted to solve for x, I could see that 4 squared is going to give me 16, so x is equal to 2. So instead of having to use the change of base formula that we covered before, doing the log of base 10 of 16 divided by the log of base 4, I can convert it to an exponential function, and without using a calculator, I was able to solve for the value for x. Okay, so again, this is a very great tool to use. So let's look at another one. Let's go backwards now. Let's convert this exponential function into a log function. Again, I have all my answers already. I don't have an x. So on this one is just to practice the opposite. Let's go from exponential to log. So what I see here, I have an exponential equation that has a base 5. So then that means that my log function or equation has to have also a base 5. See the base 5? So again, my output of my exponential function is my input of my log. The input of the exponential function is the output of my log, okay? So again, this one was just to practice that we can go from exponential to log and from log to exponential. Okay. Again, please stop me if you have any questions. So let's look at another one. Let's look at this one. We have log of base b, input 27 is equal to 3. Let's convert this into an exponential function. So my base in this problem is b. So then my exponential function is b. Again, my output of my log was 3. So it becomes the input of the exponential function. So it's b to the 3. It becomes the exponent. The input of the log becomes my output of my exponential function. So b cubed is equal to 27, and we can solve for b. We can say that, oh, 3 times 3 times 3 will give me 27. Yes? All right. So let's look at this one. The square root of 81 is equal to 9. Well, hey, but um, they're telling us that we need to convert from exponent to log, but I don't know, we don't see an exponent, but we really do. This symbol, the square root, has a exponential representation. The square root of a number can be represented as the exponent 1/2. Okay, so square root of 81 has the same representation as 81 to the exponent 1/2. So now I can convert this into a log. The base of my exponent is 81. So let's go ahead and do that. So my log has a base 81. Again, the output of my exponent becomes the input of my log, which is 9. The input of my exponent becomes the output of my log. So converting the square root of 81 equals to 9 into a log form is, again, log of base 81 input 9 equals 1/2. Okay, very, very useful tools to learn and know how to convert from logarithmic to exponential, and vice versa, exponential to logarithmic. Okay, all right. So let's look at some more properties, okay, that we like to consider. So let's look at our one-to-one property here, or our zero property, right? So we have a log of base a, and our input is 1, okay? Our answer is also always going to be 0. So remember, like I had told you at the beginning, any exponent to value 0 will give me 1. So opposite to that, if I plug in 1 to any log, my answer will always be 0. Okay, this is like the identity property. If I have a log to a base a and I input a, my answer is going to be 1. And you can see it clearly with the exponents. If I have a to the 1, that means I only have 1a. Okay, here we can use what's called like our power property that we had learned before. It's very similar. Is this log of base a to input a is 1, but we can use our power property that we multiply x times 1, which is just going to give us the x, okay? Or we can do the inverse property. Exponent to a log, you can, some people like to think that they cancel each other out. The exponent cancels with this log, leaving you just with the input x. But what really happens, it just becomes 1, okay? The logs multiply to 1. All right. So, and then our last one again that we had covered, our one-to-one property for exponents has the same for logs. If I have a log of base a with an input x equal to a log of base a, the same log, but has another value y, the only way these two logs can be equal to each other is if x and y are equal to each other. Okay. All right. So let's look at some examples. Let's solve using our properties for this. We have log of base 3 of our input 1 over 27, okay? So what I can do is, let me convert the 1 over 27 into an exponent form. So let's see. Can we do this? Can we convert our 1 over 27 into an exponent so we can solve? And hopefully the answer is yes. Yes? So here, I know that I have, if I convert it into an exponent, okay, I have a log of base 3. I can have an exponent of base 3. I don't know what the answer is, and this responds to or represents my input, is equal to 1 over 27. Yes? So again, I can convert that 1 over 27 to something that has a base 3. Okay? So what I can do is I know that 1 over 27, I am, again, skipping some steps, is 1 over 3 cubed, because 3 cubed, 3 times 3 is 9, 9 times 3 is 27. Again, move it to the top, okay? My reciprocal property, I get 3 to the negative 3. So what is my answer? For these two exponential equations to be equal to each other, that means that my question mark or my answer has got to be negative 3. Yes? So log of base 3 of 1 over 27 is equal to negative 3. Okay? All right, let's do a few more. All right, so since I'm kind of running out of time and we want to get through all of this, again, um, wanted just to show you where I got my properties from this one, okay? You can use your inverse properties again to solve. So let's go ahead and solve this one, okay? We have a log to a symbol pi to an input pi to an exponent 5. Do you see any of these properties that we can use to solve for this? Oh, so hopefully you see the first one here. Number 2, it says that I have a log of some base a and I'm putting something a into it, okay? So I have that going on. I have a log of base pi and I'm putting in pi, okay? But then I also can use this property that says that if I have x, my answer is, or my exponent, if I'm plugging in an exponent, my answer is just going to be my exponent because this is going to become 1, right? And we can rewrite it and apply it, okay? And this is the same thing as 5 times log of pi to the input pi. And that log of pi input pi becomes 1. Then 1 times 5 is equal to 5, okay? All right, how about this one? Log of 7.5 input 1. What do you think the answer is going to be? Ooh, what does it say here? Whenever we input 1, it doesn't matter what our base is. When our input is 1, what is always going to be our answer? 0, right? So our answer for this one will be 0. All right, how about this one? Log of base 90 to input 90. Okay, so what property is this one? And we got the third one again, right? So we don't have an exponent here, but we know that we have an exponent of 1, right? So you can see it here. The log of base a to input a, our answer will always be 1. Okay? All right. How about this one? 3 to an exponent of log of base 3 input 8. What is this familiar to? This one right here, right? So we have our inverse property. We have a base a to an exponent of a log of the same base, which is 3. So our answer is just going to be the input of the log, which is just 8. Yes? All right. So let's solve using our definitions. Let's put everything together. Let's solve for b on this problem. We have a log of base b input 1000 is equal to 3. Okay. How would we do it? Well, what we can do is we can convert it, right? We can convert it into an exponential definition so we can see it better. So we have a log of base b, so my base is b, so that means my exponent has to be b, excuse me. My output of my log has to be the input, the exponent of my exponent, which is 3, and the input of the log is 1000. So what base taken to exponent 3 will give me 1000? Well, that is 10, right? 10 cubed, 10 times 10 is 100, 100 times 10 is 1000. So b cubed is 10 to the third power. Yes? All right, so in my answer, b is equal to 10, had a base 10. All right, how about this one? Log of base 6 input x is equal to 5, okay? Um, so again, let's convert it to exponential. I have a base 6, so my exponential has a base 6. My output is 5 on my log, so that's my input. So 6 to the 5th power is going to give me 7,776, yes? All right. So again, a very great tool to solve for your log um, equations is to converting them to exponential problems. Okay. So again, this is just a review of our properties of logs. Um, Very similar to our exponential. So let's go ahead and solve for this one, okay? Let's solve for x. Log of base 5 of input x plus 1 is equal to the log of base 5 of input 9. Oh, I can use my one-to-one property. I have two logs that have the same, and in order for these two logs to be the same, then that means that my inputs have to be the same. So I'm using my one-to-one property, okay? So for these two to be the same, x plus 1 equals 9 have to be the same. Solve for x, subtract 1 on both sides, so x is equal to 8. Okay, always check your answers when working with the logs because we want to always be mindful of our domain. Okay, so this they do pan out, right? 8 plus 1 is 9, so the log of base 5 of 9 is equal to the log of base 5 of 9. All right. How about this one? I'll give you a few seconds to solve for this one. Okay. Log. So remember, when we don't see a base, we automatically know that this has a base 10. Okay. So since they both have the same log, again, I can use the same property again. Okay, which is my one-to-one property. Okay, so for these two logs to be the same, then that means my inputs have to be the same. Okay, 17 has to be equal to x squared plus 8. Again, we're going to be left with a quadratic, right? So we add our combine our like terms. We have x squared minus 9. Again, I hope we can factor this, or you. I'm using the square root, but I would have factored better, but we can use the square root. So we can solve for x. We add 9 on both sides, take the square root of both sides. So the square root of 9 is going to give me plus or minus 3 equals to x. So remember, you always want to check your answers. So let's plug in. Okay, if I plug in 3, 3 squared is going to be 9. 9 plus 8 is 17. Okay, that works. Negative 3 squared gives me also a positive 7. Positive 9, and 9 plus 8 is still 17. So both of them work. So both of them are solutions. Okay, the negative 3 and positive 3 are solutions for our problem. Okay, let's do this one. Let's do a natural log one. The natural log of x squared minus 3x is equal to the natural log of 18. Again, these two are the same log. They're the natural logs. So for these two logs to be equal, then our inputs have to be equal. So again, we're still using our one-to-one. So x squared minus 3x has to equal to 18. Again, I see that I have a quadratic because of the exponent of a 2 here. Okay, so again, we can factor. We can use the quadratic formula for this one. Again, factoring is always the way to go, right? So we can factor this to x minus 6, x plus 3. So that gives us two answers that we need to check. When we do our algebra on the x minus 6, x is equal to 6. For the x plus 3, we have x is equal to negative 3. So let's check. Let's check our work. Okay. Um, well, let's not check our work because we're running out of time. Let's go ahead and do this one. And I think this might be our last one. Okay. So we have the log of base 4 of x plus 6 plus the log of base 4 of x minus 6 is equal to 3. Does this look like any of these properties here? Well, I don't see it, right? But we did learn some other properties before, right? We learned that we can combine these two, okay? into when we have two logs that are being added to each other, we can condense it to a single log, right? We can write this as, and I'm gonna write it. We did several examples of this before, but again, this could be the same thing as log of base 4 of x plus 6 times x minus 6 equals 3. Okay, so don't forget those properties that we had covered before. Okay, they're always going to be come in handy. Okay, so I do have a couple of minutes. I can finish this one. Does anybody have any questions? No questions. Again, so I mean, we can finish solving for this one. So we can factor this out. So we have the log of base 4. Okay, if I do FOIL, it's going to give me x squared minus 6x, but then I have a plus 6x, which has cancels, and I get a minus 36 is equal to 3. Okay. All right. So how can we finish this? So one way we can do it is we can, again, convert it to exponential. But again, this was for practice just to show you that we can use other properties to solve for exponential functions. Okay. So thank you for joining us. Again, if you have any questions, if you want to continue working with your homework, please visit the tutors that are here available. Don't forget to sign in, okay? There's a survey, a link on your chat box. Please go ahead and do that. Help us out to see how we can improve these workshops for you. Okay. Thank you. You guys have a good weekend. Um, Hope to see you next week. Thank you.
Thank you so much, Mr. Carrizales, for presenting today. Thank you for the audience for coming and being a wonderful audience. And we hope to see you soon. Next week, we're going to go ahead and be covering, let me go ahead and share the schedule for you. Next week, here. Okay, perfect. Thank you. Uh, Also, we also have tutors, like Mr. Carter said, I was saying, if you, any of you have questions, we have tutors available who are in standby. If you have any questions whatsoever, go ahead and raise your hand, and we're gonna have a tutor be able to help you. Also, as well, next week, like we were saying, on July 16th, we're gonna be covering. Sorry, there you go. Technical difficulties right there. There we go, sorry. For the Math 1314 room, we're going to be talking about properties of logarithms and exponential logarithmic equations. And for the Math 1324 room, we're going to be talking about exponential equations and logarithmic form as well, solving exponential and logarithm equations. That's going to be on July 16th, also at 3 p.m. If you have any questions, go ahead and raise your hand and let us know, and so we can get to you. Other than that, this concludes our session for today. You have a good day, a good weekend, and be safe. Thank you, y'all. You have a good one.